Howdy, everyone. Happy Monday. Happy February. Last Friday, somebody asked me favorite places that I had in the world, and I think this has to be number one. And if anyone has seen anything more spectacular than this, please send me a chat or an email. If you look at the video right now where you see all the steaming or the spray going up, uh, that alone is almost as good as Niagara Falls. So many of you have been to Niagara Falls. I have. I've been to Victoria Falls in Africa, but nothing comes close to this. Just look at the number of waterfalls, look at the levels that are there. And this is right in the heart of the rainforest. So if you go there, you see all the rainforest wildlife, the toucan birds with the giant beaks. There's panthers running around, which you try to avoid. There's civets, which are kind of like raccoons. And they're built walkways so you can actually walk out to where that thundering falls area is, and you can walk across the whole way. And you can approach this from the Argentinian side, or you can approach it from the Brazilian side. I luckily had a collaboration with a colleague in La Plata, Argentina, and he encouraged me to go see this place, so I did. And then later on, I was invited to give a talk at a conference on the Brazil side, so I've been able to come here twice, and I'm just dazzled, even just looking at things from the ground. You can take a little boat trip to the bottom of these big falls too, but put this on your to-do list in your lifetime. It's really someplace not to be missed. Okay, so that shuts that off. And I probably have to do a stop share, which I'm doing, and I'll share again. Okay, so we're back to quantum mechanics. And where we ended last time is I told you that tunneling was really, really important, but I told you it was also very, very complicated. The main thing to note is you can solve the solutions, but to do it, you have to add boundary conditions. Not only do wave functions have to have boundary conditions and be continuous, so do the first derivatives of the wave functions. So remember, in this problem, we have a particle with not enough potential energy to overcome a potential energy barrier. In the real world, it would not get through, but in the quantum mechanical world, it can get through. So this is kind of a crude picture that I don't like very much. It kind of shows the wave coming in, going through the barrier and coming out the other side. More realistic picture is this one. Here's a wave trying to come through a thick barrier, and you can see it's pretty well died out, but maybe a tiny bit of it is going to get out at the right side. You can't really see any coming out. But where you get tunneling is if the barrier is low enough and thin enough, in other words, the X direction isn't too high to prevent it from coming through, you can get a smaller wave then coming out on the other side. And as I said last time, this can be really important in understanding tunneling electron microscopes. And so read what is in your text. Okay, so this brings us to Verner Heisenberg. And it turns out, I'll just read it here, one of the consequences of the wave nature of matter is that we can often not determine both momentum and position of a particle with great accuracy. We have already seen that particle positions are given by probabilities. And I'll try to prove this in a simple-minded way, why we can't know them both. But first, I just want to give you the quantitative relationship for the Heisenberg uncertainty principle. So up to now, I've been touting Schrödinger, saying, if we know what the potential energy function is, and if we can solve the mathematics, which we can now do with computers, The Schrödinger equation will tell us everything we can possibly know about a quantum mechanical system, atoms, electrons, and so on. But Heisenberg throws a wet blanket on it. He says, we can't know everything. And in fact, his limits are defined here. This is one of the ways to express the Heisenberg uncertainty relation, the most common way. And he says the uncertainty in momentum times the uncertainty in position, and here I've used Q instead of X, but we could have X here, has to be greater than h bar over 2. So h bar is Planck's constant over 2 pi, and so this is the relationship. Usually, when you do a problem at the atomic level or molecular level, we're going to know the mass of whatever we're talking about, say an electron or a proton or whatever. So we can fairly safely say there's no uncertainty in the mass. So in general, the momentum itself is going to be mass times velocity, and the uncertainty in momentum will be mass times the uncertainty in velocity. And so this is probably the mathematical way that you would do a problem on an hour exam, for example, if you're doing a Heisenberg type problem. Mass times uncertainty in velocity times uncertainty in position is greater than or equal to h bar over 2. Okay, so let's see where this comes from. Heisenberg would scoff at what I'm going to show you because here he had something like a 20 or 30 page paper in the Annals of Physics or some journal back in the 1920s. But I'll show you a simple-minded way why we can't know both of these things. So first, let's look at the de Broglie relationship. Again, we're talking about particles now. So the effective wavelength of this particle is h over momentum. And here we're implying that we know exactly what the momentum is, it's p. But if we have a free electron or proton or even a molecule, and it has a known momentum, which is mass of the electron times the velocity, then it is going to have one exact specific wavelength given by the de Broglie relationship. There's not going to be a range of wavelengths that we can see. There's going to be just one wavelength applicable to that electron. Well, think about the properties of a wave. If we have a simple wave, maybe this is a sine wave, where does it start? Where does it end? Well, it starts at minus infinity and it ends at plus infinity. So this means we know absolutely nothing about the position of the particle if it's a true entire wave. When we did the particle in a box, we had a contained system where the electron could not get outside the box. And so the waves were described by wave packets. We talked about doing the wave functions and probabilities, psi star psi, to figure out where the system is, but we didn't know exactly where the system is. So what I'm showing you here is if we think we know what the velocity of something is, and we think we know what the momentum is, we don't know anything about the position. So in a way here, what we're saying is delta P is equal to 0, then delta Q is infinite. So we just don't know about this. So as I said, systems we've looked at up to now, we've had confined systems. So particle in a box, we had a wave something like this. We could use the wave function by writing the wave function squared, have it be a probability function, and we could see where the maximum probabilities would be and where the minimum probabilities are. So I think this probably also adds to what I said at the beginning of the semester. We now know even less about where an electron is. If it's pretty much free to fly around in all space, it can cover a wide range of coordinate at any given time. Just as a last thought, in case you play baseball or something like that and you're worried about figuring out where the ball is, you don't have to worry too much. If you take a 1 pound baseball, the uncertainty in velocity is going to come out to be something like 10 to the minus 28 meters per second. So not even measurable by electron microscopes if we had to worry about, well, here we're talking velocity, but nothing measurable. On the other hand, a typical uncertainty in an electron in the velocity could be something like 10 to the 5th meters per second, or that's 100 kilometers per second, or 62 miles per second. So pretty significant uncertainty in the velocity that an electron might have. Okay, let's see if there are any more chats. Okay, I have a couple of people like the Iguazu Falls. Okay, now we come to another very, very important aspect of what you can do with wave functions. We've seen that we can take the squares and they will be functions of the probabilities, but we can also use them to calculate averages. And to do that, we have to have operators. Almost the first day of class, I introduced you to operators. We first had the del squared operator, which you remember involves taking the second derivatives of x, y, and z in polar coordinates or spherical coordinates, r, theta, and phi in angular coordinates, spherical coordinates. But we also had an operator, the Hamiltonian operator, which can also be called the energy operator. And notice that the Hamiltonian operating on psi gives us E psi. If you read your book, by the way, and I'll try to mention this later, and it won't be a terribly important aspect in the course, but when we have a situation like this, that the Hamiltonian operating on something directly gives us a constant times the wave function, the psi is called the eigenfunction or the eigenvector, and the E, capital E, is called the eigenvalue. That's a mathematical solution for a characteristic value. But we'll come back to that later. Okay, so what is it we're going to do now? I'm going to give you a bunch of symbols, operators, and these are the operators. And when we operate on this wave function, we're going to find that we can put the result into an integral and then calculate the average value. So we will be able to calculate average energy, average kinetic energy, average momentum, average position squared. I didn't write it here, but an interesting one is the average momentum squared. As we're going to see, the average position is often 0 because particles are going to the right and to the left. And similarly, average momenta are often 0 because particles are often going to the right and left. So squares of those are going to tend to be more interesting. Okay, so whenever we have an exam, I'll be sure to give you whatever operator you need. I wouldn't give you position or position squared operators because they're just multipliers themselves, as we have here. Okay, well, here's our definition for finding an average value. The average value we're going to call an expectation value. This is what we're most likely to get when we go through this process. So we're going to find the expectation value of something I'm generically calling S here. So I'm going to use the symbolism S with a bar over it. That'll mean the average S value. Other nomenclature, this is called Dirac nomenclature, has these carets around it, or a bracket around it. I think your book might in fact use this. Sometimes books put these expectation values into script form and other form, but for our notes, I'm going to use the S bar notation. All right, so we want to find S bar. This might be, say, average momentum. It means we take the operator for that system or for that situation, say the momentum. and then we operate on psi. So we do a differentiation first if a differentiation is required. So I don't think I wrote that clearly enough in the notes, and you might put a bracket under SOP psi. You do this part first, SOP psi. When you're done, you multiply it times the sine star, and you integrate it over all space. And here I've written this as d tau, indicating you can do it in 1 dimension, 3 dimensions, umpteen dimensions. This is a generic formula. Dirac notation would write it like this, psi star S op psi. And oftentimes we identify wave functions by just their subscript. So this might say I S op j, and then it has these brackets around it. And we're not going to use Dirac notation, but it's probably more commonly used by deep in the wool quantum mechanicists. And the left part, this is called a bra, and this is called a ket. So it's a bracket or a bracket that we put around this thing. Okay, one more chat question. Okay, repeat what you do first. You do the right side of the integral first. S op is often an operator that requires taking a derivative. For example, if we're doing momentum, this is what you take the derivative of. So you would take d dx of the wave function with this multiplier in front, and then you multiply it times psi star. I'll go through an example below, but you do this step first. If we're doing position or position squared, since those are multipliers, you don't have to worry about what you do first. Okay, so let's do a very simple example. We'll find the expectation values for the coordinate for a harmonic oscillator in its lowest state. So remember the harmonic oscillator, we have this thing going back and forth all the time. Its equilibrium position is x0, goes to plus x, it goes to minus x. So we don't even have to do quantum mechanics to know that on average, this is going to wind up with an average value of x0. But let's do the mathematics to prove that this is the case. Okay, so here's the wave function psi 0, which you would be given, and I've given you this before. It's got a normalization constant in front, and then this is this exponential form. The energy levels just parenthetically come out looking like this. What we have to do mathematically is then we multiply x times psi 0, and then we multiply that product by psi 0 star. Psi 0 star is the same as psi 0 because there is no imaginary term. So this is the integral we have to solve. And it's a rather unpleasant integral, but note that we're going to split it into two parts, which are going to cancel each other out. I mentioned this last week. Make sure you know how to multiply this exponential times itself. You add the exponents together. So this exponent times its, or plus itself, gets rid of the 1/2, and you have e to the minus half of x squared. Okay, so this is what we have to solve. We have this integral from minus infinity to 0. Notice that this will always be minus because x is minus and the exponential term is positive. For the integral from 0 to infinity, x is positive and the exponential term is always positive. And since the terms here are identical, the magnitudes are going to cancel out. I think I showed you almost exactly the same thing when I showed you orthogonality between psi 0 and psi 1 for the harmonic oscillator last week. So this is the same kind of thing. You see an odd function from minus infinity to from minus infinity to infinity, and so you know it's going to cancel out. Okay, well here's a picture of the wave function. If you just want to look where the system is going to be, you can see the maximum is at x equal to 0 in the middle, but it's going to spend just as much time at minus x as plus x, and so our average value is going to come out to be equal to 0. Someone asks, does alpha have to be real for the equation to work? alpha is a constant, and so it wouldn't matter, because whenever we look at probabilities, even if you had an I in front of the system, when you take the psi star psi, the i's would cancel out, so you would get rid of that. So alpha is constant, but I mean, if it weren't in some other case, it really wouldn't matter. It's outside the integral. The integrals themselves cancel out. Okay, well, let's do a more interesting case. And this is what is going to be the average value of x squared. So I contend that this is more interesting because this will give us an idea how far away the system is on average from x equal to 0. Okay, someone asked, what's the point of ED? I don't know what ED means. The point of all this is that we have an odd function and it cancels itself out. So we get an answer for the expectation value here that comes out to be 0. Okay, well, let's do x squared. So here is our function squared, and this time we do have to integrate it. Again, in integral tables, you typically will not find definite integrals from minus infinity to infinity. You'll find them from 0 to infinity. So when we look at this function, we'll see it's an even function. And so it's going to have exactly the same positive magnitude at minus x values as it will at plus x values. So minus x squared is positive. The exponential is positive. And the right side, the right integral is also positive at all values. So we know the integral on the left is equal to the integral on the right. And so we can write the entire problem we have to solve has a 2 in front of it, but now we only integrate from 0 to infinity. Again, I think we did something very similar to this last time when we wanted to find the normalization constant of psi 0 or psi 1, I don't remember. Okay, well, this is a little bit more difficult or confusing integral to get from an integral table. If you go to the integral table, this is what you will find. And what you would recognize is that we would be picking the case for n equal to 1. So we have x to the minus 2, meaning n is equal to 1. And the a here is equal to our alpha. So that's what I've written. We have n equal to 1, a equal to alpha. But this general integral formula would work when n is equal to 3, for example. You could have x to the 6 times e to the minus x squared, and this would still work. If you look at the solution, we have to keep in mind n is 1, and then we see here it says you go 1 times 3 times 5, et cetera, until you get to 2n minus 1. Well, 2n minus 1 is only 1, so that means we really have to stop at 1. So don't be confused by the fact that the 3 and 5 there, that's just to give you a hint that you keep on going in case n is larger. So in our case here, we would just use the 1 over 2 plus 1 plus 1 over a to the first power. So this is what we come up with, 1 over 2 squared. A is alpha to the first power, and then pi over a square root of that. Here again, I'm impressed by the mathematicians who come up with integrals like this. I wouldn't want to try to be taking things to infinities and finding limits and so on. So I'm glad somebody's done this for us. But we have the table, we look at the comparison of the cases, we compare the terms, and we find out indeed that x squared bar, the average value of x squared, is a positive value 1 over 2 alpha. Here's the definition of alpha. Well, right now, this wouldn't mean very much to you because we're not putting in force constant values, mass values, and so on. But the point is, we could calculate what the average value of x squared is. Now, if you think about what this is, and I'll come back to this later, if I took the square root of this average value of the x squared, that will give me the absolute value of about where we expect x to have its maximum values at either plus x or minus x. We're not restricted to just plus x values, but it could have maxima at both plus x and minus x. Okay, checking the chats again. Someone asked they thought psi equals psi star only if there are no imaginary numbers. That's correct. Someone wrote E0. Someone wanted to know why I wrote an equation for E0. That was just parenthetical to remind you that we have a corresponding energy level for it. So anyway, the question about alpha having I's or no imaginary terms, it's a moot point. It doesn't matter if it's there or not. Okay, let's do average momentum. And unfortunately here, again, the result is going to be boring. If we have the harmonic oscillator, half the time it's got a momentum to plus x, half the time it's got a momentum to the minus x. So we know the answer is going to be coming out to 0. But let's do the mathematics. Okay, so average value, we have the operator P of x operating on psi 0. So notice the first thing you have to do is take the derivative with respect to psi 0 with respect to x. You can pull the constant term out in front. So the operator is h bar over I times d dx of whatever follows. So this is the integral we have to solve. So unfortunately, this forces us to start taking the derivative of this nasty exponential again. We've done it once before. So it comes out to be the exponential term times we have to take the derivative of the exponent, from which we get a minus 2 alpha x over 2. And that reduces down to minus alpha x. So the alpha part is a constant. We can pull that totally in front of the integral, and we're left with this integral again. Well, this time I'm not going to prove it. I think all of you by now should be seeing that whenever you have an odd integral from minus infinity to plus infinity, this will be negative at all minus x values. It'll be positive at all positive x values. So the total area under the curve will come out to be 0. Negative area for minus x, positive area for positive x, and it totally cancels out. Okay, so average value of the momentum is 0, not surprising. I'm not going to do px squared in class, but it is solved in one of your practice problems. And by the way, that's something I encourage all of you to start doing. At the end of the sections after quantum mechanics and atomic structure, there's a whole bunch of practice problems and more practice problems. This is one of them. And so those are more like what you can expect to see when we get around to having the first exam, which is still several weeks away. Another chat. Okay, someone asks, how do we know whether something is even or odd? This is an odd function because the exponential term, the first term, is even. No matter which x value you have, it's positive. X is odd because it changes sign in going from minus x to plus x, and then we have an even function again. So an even times odd times even comes out to be odd. So you look to see whether this changes sign in going from minus x to plus x. If it doesn't change sign and you have equal magnitudes, then it's called an even function. That's the case we had up here. So this magnitude and that magnitude were the same, so this was an even function. Right here, we have an odd function because of the change in sign. Okay, so good news is maybe even by Wednesday, we will finish all the background mathematics for quantum mechanics. But the bad news is some of what we have left to go over through is some of the hairiest stuff. I've condensed it somewhat to some degree so we don't waste time on things that chemical engineers and chemists don't care a whole lot about. And a lot of this is actually related to atomic structure, things that mostly physicists are interested in. Okay, so our topic is going to be molecular motions, and we'll talk about translations, vibrations, and rotations, and the mathematics of that. But before I do that, let me just jump to the next page and mention a couple of things that you may run across in your textbook and raise you questions. So these mostly have to do with nomenclature, and I'm not going to be asking you exam questions on it, but if you run into terminology you don't know, then this will identify it here. If I have an operator operating on the wave function and I get a constant times the wave function, then we call that the eigenvalue. Eigen is the German word for characteristic. The wave function is called an eigenfunction. So we've already talked about the Hamiltonian operator. And so the Hamiltonian operator working on the wave function is equal to an eigenvalue, which represents all the possible energy levels times the eigenvector. Okay, so that's one thing. The next thing you might run into your in the book is it'll tell you operators have to be Hermitian. And the rule for that is that they have to have real eigenvalues. You cannot have energy solutions without an I in there. And then to totally confuse you, the book will tell you something like this, that you can be sure that this is the case, that if you write your operator formula like this, it's going to be equal to that. So it doesn't matter which order we take psi star psi. Here, I've written phi as a possible second kind of wave function that it could be. If you reverse the order, then the mathematics would still come out to be the same. Turns out that this is really quite important. Something like almost 50 years ago now, I wrote some computer programs which have become quite famous and are still quite used for solving certain kinds of potential functions. I initially was confused by what I had to do with making operators Hermitian, and I had the signs of some of my matrix elements incorrect. So once I got that corrected, I got some nice results from the computer program. But again, you don't need to worry about the details, but I just want to point out that these are some of the things you might read about. The other thing I wanted to point out is that we talked about finding things like the average position squared, and we saw that it was different from the average of the square of the position. This is called the variance of X when you have an expression like this. And this is related to standard deviation. As engineers, I'm sure you've run into standard deviations a lot in your own measurements. So we're writing this as sigma x squared is the variance, and the standard deviation is the square root of the variance. And again, as you know from previous stuff, statistically it means if we want to know what the x value is within a standard deviation. 68% of them will be within one standard deviation. 95% of the numbers would be within two standard deviations. So practical standard deviation measurements can carry on to the results from quantum mechanical calculations. Next time, I'll probably have a chance to tell you how we can use variance to actually give you a quantitative feeling for the Heisenberg uncertainty principle. We'll use the variance of X and we'll use the variance of momentum, put them together, and it'll come out to be the magnitude that we have in the Heisenberg uncertainty principle. Okay, so back here again, we've talked about translations. We examined them as a particular box, and so fairly straightforward process, but we also saw that if the box gets to have infinite width, then we lose all the quantization that we have. Someone asked if the standard deviation formula still works when the function has multiple maxima. Yes, because we're not talking about maxima in positions here. Where did we go? We're not talking about maxima. We're talking about the average value of X. So the average value of X is not necessarily the maximum value of X, of which there may be many. There may be many maxima. Okay, just quick reminder about the harmonic oscillator again, and I'll give you a little bit more embellishment again. It turns out knowing the solutions to the harmonic oscillator from the very lowest energy way up is a very important aspect of understanding quantum mechanical problems when we do computers. It turns out that oftentimes when you write approximate solutions, you will make it as a linear combination of harmonic oscillator solutions. So I don't know if that makes sense to you, but I'll try to expand on that at some later point. But for now, I'm just justifying why it's really important to know that we have these solutions. The harmonic oscillator solution is one of the very few that can be solved exactly. The very first very good quantum mechanics book was written in 1935, 9 years after Schrödinger. The authors were Linus Pauling and E. Bright Wilson. I'll tell you more about E. Bright Wilson and vibrations later on in the course. Linus Pauling got 2 Nobel Prizes, one for chemistry and one for the Peace Prize. He was also a strong advocate of telling you that you should drink lots of orange juice to keep away from getting colds. That's not been proven, and some people debunk it, but he's famous for that. Anyway, why I'm mentioning this is that in this book, they devote 40 pages of this 500-page book or so to telling you how to solve the harmonic oscillator. And so don't be surprised when you see that these solutions are fairly complicated. They depend on something called Hermit polynomials. Now, you engineers run into a lot of polynomials. Have you run across Hermit polynomials? I'm looking at James. He doesn't shake his head one way or the other. He doesn't know, so maybe not. So you're going to learn about Hermit polynomials when I look at these solutions. Okay, here's a chat answer. Okay, Alexis doesn't think so. So, okay. So this will be new stuff for you. All right, just a reminder what the harmonic oscillator is. We have a spring vibrating back and forth. Here's the force. What you should know is the definition of the force is the negative derivative of potential energy with respect to X. We can integrate that after we get the dV on one side, the dx on the other, and we get 1/2 kx squared. We throw away the constant term that we don't need. So that's the quantum mechanical problem that we have to solve. And you remember these are the energy levels we got. They were all equally spaced. We had a 0-point energy of 1/2 h nu, which comes out to be h bar over 2 times the square root of k over m. So when we do spectroscopy, and this topic, as you remember, I'm just saying topic is molecular motions. We're going to talk about vibrations of molecules in a bit. A typical spectroscopic transition would be from quantum state V0 to V equal to 1. This is pretty much what you looked at when you took infrared spectra in organic chemistry lab. And so the vibrational frequency would be 1 over 2 pi times the square root of k over m. Now, this is what you have strictly for a diatomic molecule. But even if you look at bond stretching for polyatomic larger molecules, this formula would still pretty much hold. If you put in typical values of force constants for molecules and masses involved, you find that the vibrational frequencies is about 10 to the 14th seconds to the -1. So really, really fast. So if I'm doing it, my math right in my head, it's 100,000 billion times per second that a typical bond vibrates when you look at it. Okay, and then the vibrational frequencies we saw are equal to V plus 1/2 times h nu. The 1/2 is what gives us the 0-point energy. We can't start at energy 0. Okay, so we know all about the energy levels, but I've only given you 2 of the lowest harmonic oscillator functions. And so this is the general formula for the wave functions. I don't think I'm going to have any cases where you need to apply this, but as I said, an understanding of the harmonic oscillator can be really important in physics and chemistry. So I think it's worthwhile that we look at this. All right, well, everything here is pretty easy to understand. We're going to start off with quantum state psi 0, where quantum number V is 0. In that case, we would have 0 factorial here. In case you haven't done 0 factorials in chemical engineering, 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1, and so on. And then it's 2 to the vth power. If we're doing psi 5, it's 2 to the 5th power. So all of this bloody thing is the normalization constant. And then notice on the right, we have our familiar e to the minus alpha x squared over 2. So all of these functions are going to have the same exponential term with a minus alpha x squared in there. And alpha, as always, is going to be what I've written here. I do have to note the version of the book we're using right now defines alpha differently. So the textbook alpha is defined like this. So whenever I write something as alpha, the textbook will write it as alpha squared. So they would put an alpha here and an alpha squared there. Either way, the functions would come out looking the same once you put in the m's and k's and h bars and everything else. Okay, so these h sub v's are the Hermit polynomials. And I'll first show you what they look like when you're dealing with just some coordinate y. H of 0 is y. Sorry, h0 of y is 1. If you go to h1, it becomes 2y. If you go to h2, it becomes 4y squared minus 2. If we want to go higher, as I'll show you, we have a recursion formula that lets you calculate any of the higher polynomials. Okay, so h0 for alpha to the 1/2 x stays 1. h1 becomes this. We have to replace y by the alpha to the 1/2 x. And then in the next one, the y squared turns into 4 alpha x squared. So we can generate these as we go along. Again, I'm not going to make you do any of these, but you might find it interesting that there's a way that these can be generated. A very common way that a computer program will approximate a wave function will be to maybe take the first 50 or 100 harmonic oscillator solutions and find the best linear combination of these that it can that'll give you the correct answer. So being able to get a lot of these can be important. Okay, well, here's our recursion formula. It says h sub v plus 1. In this case, let's say v is equal to 1. So we would have h2 minus 2y h1 plus 2v of h0 is equal to 0. And if we jump a page, you'll see that this is what we get here. If you go back to what I have in the notes, this just confirms what I gave you. And once we have 2 of these Hermit polynomials, we can generate all the others. And of course, we can tell the computer how to generate all of these. Sometimes people even use thousands of these Hermit polynomials and functions to generate approximate solutions. In between, I stuck a little bit prettier picture of how we like to represent the harmonic oscillator functions. You'll remember what I said is we'd like to draw the potential function. So the curve here, the parabola, that's the potential energy. Each of these horizontal lines is a possible energy level. So this is E0, E1, E2, E3. E0 has corresponding wave function psi 0. E1 has corresponding solution psi 1, psi 2, psi 3, psi 4, psi 5, psi 6, psi 7. Notice how they all get more and more squigglier as you go up, and that indicates more and more kinetic energy that you have. Now there's one or yet another very strange feature here that I can point out to you about quantum mechanics. So each of these horizontal lines is capital E, and this parabola is capital V. So if E is equal to capital V, that in classical mechanics would say that the kinetic energy is 0. So anything to the right of this point, or to the left of the point over here, should not exist. But here's the wave function, and the wave function squared is a probability function. So it tells us that the harmonic oscillator can go outside this potential energy curve and actually exist. So this is a violation of classical mechanics, but we want to be doing that anyway because we know classical mechanics doesn't work for quantum mechanical systems. This is a little bit subtle to understand, but just remember E is supposed to be equal to T plus V. And if I pick this point that E is equal to V, T should be 0 classically, but it's not. The system can keep on going outside. And this is true for all of these. On the other hand, notice that the curve goes to 0 very quickly, or close to 0. So the amplitude of the harmonic oscillator in this lowest state is roughly from here to there. When you get up here, it's got a much greater amplitude. It's going to have a lot greater kinetic energy. But the potential energy curve kind of gives you the amplitude of how much vibration you're going to get for a chemical bond or a vibrating string, for example. Okay, let's finish up on, we don't have time to finish up, but let me just say a couple more words about the vibrational aspects of the problem. All of the wave functions for the harmonic oscillator are orthonormal. For chemical bonds, the force constants are typically in the range of 100 to 2000 nanometers newtons per meter. People such as I hate those units because molecular bonds increase by picometers and not by meters. So why do we talk about newtons? So we tend to use units of millidynes per angstrom, and I'll tell you more about those later. Those will range from about 1 to 20. But before I quit, I just wanted to show you a typical calculation. So if we're going to look at a hydrogen atom in an organic molecule vibrating, attached to a heavy molecule, the hydrogen has a mass of 1 atomic unit. If you divide it by Avogadro's number, you'll get the mass in grams. If I plug that into the vibrational frequency that I showed you above, we get 8.7 times 10 to the 13th seconds. So just a little bit ago, I told you the vibrations were about 10 to the 14th per second. In organic lab, and what everybody else uses now for infrared spectroscopy, we use units of wave numbers. And you can get from seconds to the -1, which are also called hertz, into wave numbers by dividing through with the speed of light. So when we do that, we get 2910. So that's your typical carbon-hydrogen bond stretching frequency that you're going to have for an organic molecule when you do that. The 2910 is exactly the reciprocal wavelength that you have for this vibration, but it's also frequency divided by the speed of light. Okay, well, I've run over a bit. I hope you like the pictures of the waterfalls. Do put it on your list of things to do. I didn't mention, but I don't think you can ever drive there. You have to fly. They didn't used to have roads, but enough people wanted to see it that they built a little town and built an airport that you can fly to. And I think it's just called Iguazu Falls as the town. The nice thing is there's a nice 4-star Sheraton hotel right there that a taxi can take you to. It's not terribly expensive, and you can walk right into the rainforest and walk right into the middle of the heart of where all the falls are. Just really a spectacular thing. That Sheraton is on the Argentina side. I don't remember the name of the hotel on the Brazil side, but it's also a very nice hotel. Okay, well, have a good week and stay healthy. One more chat I see, and thank you too.